You know, there's this incredible, hidden engineering tool that literally shapes the world around us. We're talking everything from the phone in your hand to the bridges you drive across. It's called the finite element method, and it's how we solve problems that seem, well, completely impossible.
To really wrap our heads around this, let's start with a really big question. Think about this for a sec. How on earth do you test a skyscraper in an earthquake before you've even built it? I mean, how do you know a new airplane wing can handle insane turbulence before you've spent billions of dollars building the actual plane?
Right, so we're tackling impossible problems here. Because obviously you can't just build a test skyscraper and then, shake it until it falls down. The answer's way more clever. It's about a whole new way of looking at the problem.
And here's the thing. The answer isn't some single, gigantic, mind-bendingly complex equation. Nope. It's actually a brilliantly simple idea. See, for objects with really complex shapes and forces, there just isn't one perfect formula that can predict how they'll behave. The real world is just too messy. So, the solution is to completely change how you look at the problem in the first place.
The core idea is right here. It says the basic principle is that the object of interest is divided into a certain number of regions. That's the secret sauce. You take a super complex object and you just break it down. You chop it up into a huge number of small, simple, and totally manageable pieces.
And to really get this, let's use a really simple visual analogy, because this is all about the power of simple pieces.
Okay, imagine you have to find the exact area under this weird, curvy line. There's no easy geometry formula for a shape like this, right? It's exactly like trying to figure out the stress on some oddly shaped car part. It's just way too complex to solve in one go. So what do? We fill that complex area with a whole bunch of simple rectangles. We all know how to calculate the area of a rectangle, right? Length times width. So by adding up the areas of all these super simple shapes, we can get a remarkably accurate approximation of the total complex area. This, right here, is the core magic of FEM.
All right, so now that you get the big idea, let's learn the official language. Don't worry, every one of these fancy-sounding terms maps directly back to our simple curve and rectangles example. It's easier than it sounds.
First up, discretization. Okay, it sounds technical, I know, but it's just the fancy name for the process we just did. Breaking down a big, complex problem into a finite number of small, simple pieces. It's literally just the act of drawing the rectangles.
And what do you call those pieces? Well, each one is called an element. In our analogy, every single one of those little rectangles is one element. In a real-world simulation, an element might be a tiny cube or a little pyramid that makes up a small piece of a much larger structure.
So how do all these elements connect? They connect at specific points called nodes. Just think of them as the corners of our rectangles. These nodes link everything together, forming a complete network that engineers call a mesh. Now this brings us to a really crucial rule, and it's so simple. The smaller the element, the more accurate the result. Think about it. If you use way more teeny-tiny rectangles, they're going to fit that original curve a lot better, giving you a more accurate answer. It's the exact same in engineering. The more elements you use, the more realistic your simulation becomes.
Okay, so we've got our mesh of elements and nodes. But here's where it gets really clever. Those nodes, they aren't just static connection points. In a simulation, each node represents a point on the real object that can actually move. It has flexibility.
And this potential for movement has a name: degrees of freedom, or just DOF for short. It's basically a measure of how many different ways a node can independently move or rotate in space.
And in our three-dimensional world, any single point, any node, can have a maximum of 6 degrees of freedom. Just 6 fundamental ways it can move.
And here they are. It's actually pretty intuitive. You have 3 translations. That's just moving up and down, left and right, and forward and backward. Then you have 3 rotations, which is tilting, turning, and spinning around those same 3 axes. By calculating these for every single node, engineers can predict exactly how the entire object will bend, twist, and deform. Okay, so we've got the theory down. Now let's see how this all builds into a practical workflow that engineers use every single day with some seriously powerful software. The whole thing really boils down to a few key steps. First, engineers create that mesh. That's our discretization. Then, they tell the computer what the object's made of. Is it steel, plastic, concrete? After that, they apply the real-world forces, or loads. That's the shake from the earthquake or the lift on an airplane wing. They decide what info they need to get out of it, and then finally, they hit solve and let the computer run all the numbers for every single element.
So let's bring this all the way back to where we started, back to that skyscraper and that big, impossible problem. So when engineers need to test that skyscraper, they don't analyze one massive and possibly complex structure. They just can't.
Instead, they digitally test millions of simple, interconnected elements that make up the building. They apply those virtual earthquake forces to all the nodes and see how all those tiny pieces stretch, compress, and move together. By solving the problem for each tiny little piece, they solve it for the whole thing.
And that leaves us with a final thought. This method of breaking down the impossibly complex into the simply manageable is used everywhere. So the question is, what other big challenges, in medicine, in climate science, anywhere, what other big problems could we start to solve if we just learned how to see them one small, finite piece at a time?